also interested in the theory of universality and the relation between science, culture, and language. Welcome, Gemma. We're just waiting for our... Oh, okay. Yeah. So we are ready. We are on YouTube and Facebook. Everybody can watch you. So welcome.
Thank you, Gemma.
And, thank you. You can start.
Okay. Well, thanks a lot for having me. And I'm sorry I cannot be there in person because of some personal reasons. Let me share my screen. I hope that works. Is this all right?
Yes, it works. Yes.
Okay. So I'd like to start by telling the story of that has to do with spin models, by which when certain spin models, like the ones on the left, which is supposed to be a 2D Ising model, are seen in the appropriate light, then they can pretend to be Ising models on with higher dimensional spins, or with many body interactions, or on a high dimensional lattice. Slightly more precisely, the 2D Ising model with fields can simulate any other spin model. And this is a property that not only the 2D Ising model with field has, but in fact, most subsets of non-trivial spin models have it too. Similarly, some machines, as you know, namely, you can fix a Turing machine, and that suffices to let it run any algorithm. Okay, so there's a sense by which a fixed Turing machine can pretend to be any other Turing machine. And also similarly, there are certain families of machine learning models, particularly deep Boltzmann machines, first restricted Boltzmann machines, deep Boltzmann machines, deep belief networks, and others, that despite being a relatively simple class of machine learning models, they suffice to approximate any function in a target set. So in a similar sense, they can also pretend to be any such target function. These three examples I just gave you are all called universal in their respective domains and are similar structures, have some similar properties. For example, their power comes from some hidden variables. In the case of spin models, that would be auxiliary spins, whose value can be tuned so that the 2D Ising model with fields can pretend to be a 3D Ising model or a Potts model. In the case of Turing machines, these extra variables are the additional part of the input that's used to describe the target Turing machine. In the case of machine learning models, the extra variables would be the so-called hidden units, whose parameters need to be chosen or learned so that that machine learning model mimics or acts as or is approximately equal to the target function in the visible spins. There are other similarities as well. It seems that when each of them crosses a certain minimal level of complexity, then they reach this universality. So there are several similarities. And what I'd like to understand is how precisely they are related. I think it's a worthwhile question because some are very well understood, such as universal Turing machines. Some are new, like universal spin models. And for some, we have characterizations like universal Turing machines. For others, not necessarily, such as for Turing machines. Now we have full characterization for spin models. Or in some other cases, the characterizations are somewhat not unified, such as for machine learning models. I believe it is worthwhile to consider this question. And I would also like to understand how they relate to notions of what we call unreachability, which encompass things like uncomputability or undecidability. And I'd like to share with you what I think is the link between some forms of universality and unreachability. So overall, this talk will be about our endeavors to understand the scope of notions of universality across physics, computer science, machine learning, perhaps slightly beyond, as well as their connection to notions of unreachability. So my name is Gemma de las Coves. I moved to Barcelona last year. I worked in Austria before. I spent 17 years in Germany and Austria. And I'm now an ICREA professor at the Pompeu Fabra, surrounded by people with very different expertise. And I'm enjoying this new time, but I may be also looking for new people to work with soon. So more precisely, I would like to start by sharing with you some of the ideas that go behind these efforts. And then I'll try to be more concrete and show you how we have compared spin models with automata, then spin models with machine learning models, and finally a more ambitious approach by which we came up with a framework for universality, more of a top-down approach as opposed to 2 and 3, which are more bottom-up. In any case, I'll just try to share the basic ideas. All right, so let's start from the beginning. What does universal mean? Well, it is an adjective that means relative to the universe. And as a frozen metaphor, it means all-encompassing. Slightly more formally, mathematically all-encompassing can be expressed as follows. Given a collection of objects, C, and a relation R that lands in C, so a relation is a subset of the Cartesian product of two sets. When I say that it lands in C, I mean that the second component of this Cartesian product is C. U, which is something, some element, is called universal if U is in relation to C for all elements. Excuse me, if U, C is in R for all little c in big C. Okay, so this is a definition of the word universal. So again, this is trying to make precise the idea of universal as all-encompassing. And it says that given a collection C and a relation R that lands in C, something U is called universal if this something is in relation to every element in C. Okay, if U, C is in the relation R for all elements little c in big C. So what's interesting to note is that universal is relative to a collection and a relation. Okay, so there's no sense in saying that something is universal without referring to such a collection or a relation. So all is qualifying the element of this collection, and encompassing refers to the relation R. Okay. So this is all very weak. In fact, this definition is way too weak to make progress in helping us establish the precise links between the notions I showed you at the beginning. But it suffices to raise this question. If something is universal or purports to be universal, does it also encompass a negation of itself? Well, that's problematic, because if it is supposed to do so in a consistent way, then it will encompass itself if and only if it does not encompass itself. This paradox is very powerful. There's usually no, I'm not sure if I should say no decent way out in science, but it certainly has devastating consequences in science. We will see some of them soon. And this is the essence of unreachability. Namely, in my words, the fact that no system can thoroughly talk about itself. So nothing can be ultimately self-contained. You see, there being a universal thing for a set is a way of containing the entire set. But that universal thing must be outside of that set if things are to work consistently. And if it is outside of that set, then the set itself is not the entire story. You need the set plus the universal thing. And if you then try to include the universal thing, you are off into an infinite regress. Okay, let me not get ahead of myself for the moment. Let me try to explain this statement of unreachability. So that no system can thoroughly talk about itself, let us try to explain it for the simplest case, namely in which a system is nothing but a set S. And talk means to describe an attribute of the set S, which is a function from S to 0, 1. So that's a binary attribute. For example, you can imagine that S are the natural numbers, and the attribute is being a prime. Well, every number is either composite or prime. So all composite numbers would be mapped to 0, and all prime numbers would be mapped to 1. Or the attribute could be being odd. And all odd numbers would be mapped to 1 and all even numbers to 0. Or it could be being larger than 50 million, and so on. Now, crucially, we identify the attribute, a given attribute f, a given such function, with its extension, which is nothing but the set of elements where it is true, or the set of elements of S which are mapped to 1. For example, the attribute of being a prime would be identified with the set of prime numbers. Or the attribute of being a multiple of 5 would be identified with a set of multiples of 5. Now, such a set is a subset of S, right? This is a subset of S where the attribute is true. Therefore, it is an element of the power set of S. Okay, this curly P here denotes the power set, which is the set of all subsets. So we are identifying F with an element of the power set of S. Right? For example, assume that S had only 3 elements, A, B, C, a finite set. Then the power set has 8 elements. It always has, so the cardinality of the power set is always 2 to the cardinality of S. So it contains the empty set, the element with a single element, the element with 2 elements, and the element containing it all, kind of the improper set. And imagine that the attribute is being different than B, or not containing B. Then all subsets that do not contain B would be identified with such a function. Okay, now the key of the argument is that a set can never be put in one-to-one correspondence with its power set. Therefore, a set can never encompass its own attributes. Okay, so let me try again. So there never is a surjection, or in particular, there never is a bijection. I mean, there is an injection clearly, right? But there's no surjection. Surjection means a function that sees the entire codomain within the entire arrival set, right? So there is no surjection from a set to its power set. And we just agreed that the attributes are identified with a power set. For this reason, a set can never encompass its own attributes. So that this is the case for finite sets is obvious, because the cardinalities do not match, right? As I said earlier, the cardinality of the power set of S is just 2 to the cardinality of S. But Cantor's insight is that this is also true for infinite sets. Remember, the cardinality of the naturals is strictly smaller than the cardinality of the reals. Why? This is usually proven by the so-called diagonal argument, which is an argument of self-reference and negation. More precisely, you assume that there is such a surjection, write it down in a table with kind of the tags, namely naturals, attached to each real. Consider the diagonal, which is a form of self-reference, and flip the diagonal, which is a form of negation or applying a function without a fixed point. And the result is a new element which was not in the list, so that's a contradiction. So you must reject the assumption that there was a surjection in the first place. So this is saying that self-reference and negation escapes the system S, cannot be captured from within S. We've just seen the example of a set and what regards the cardinality of sets, but in fact, this argument is very powerful in as much as it can be reincarnated in many scenarios. For example, in plain language, if you say this sentence is false, you run into problems. The uncomputability of the halting problem is usually proven by the same argument of self-reference and negation. You assume that there was a machine that computes the halting problem, feed it its own description finally negate or the outcome, or have it loop forever if it halted, and halt if it entered a state where it would loop forever, and conclude that this perverted machine halts if and only if it does not halt. So that's a contradiction that we don't want to accept. So we end up rejecting the existence of that machine in the first place. It's the same structure. Gödel's first incompleteness theorem provides a sentence that says, I am not provable. We don't want to, so we conclude that we cannot decide whether it is a theorem or not of that formal system. And so that formal system is not consistent and complete at the same time. Russell's paradox, well, people used to believe that for any property, there would be a corresponding collection of elements with that property. That's naive set theory. But Russell provided a property, namely, he asked us to consider the collection of the set of all sets that do not contain themselves. And this property is problematic because it contains itself if and only if it does not contain itself. And you expect that a set is such that its elements, so that other objects are either in or out of the set. You don't want to accept that it's in if and only if it is out. So you conclude that that collection at the beginning was not a set. Tarski's undefinability of truth is similar. There cannot be a predicate that provides such a truth predicate that works in all cases, because you could feed it its own description and negate it, and you would be in trouble. Or Cantor's theorem is based on the same idea. So it's also very far-reaching in the sense that it cannot be fixed. If you consider a set and its cardinality and then its power set, and that's strictly larger than that of S, but this is now the beginning of a new story, because the power set of S is of a strictly larger cardinality, and so on, and this doesn't end. So in particular, this implies that there are infinitely many types of infinity. Before Cantor, people used to believe that infinity was a thing. It's more of a universe. And there's no such thing as the largest infinity. And what's wonderful is that there's a little known theorem in category theory called Lovier's fixed point theorem that makes precise how all of these are instances of a common structure. So it's a theorem that has these examples mentioned here and more as particular instances. And even more, at least according to some introductions to metaphysics, the paradox of self-reference and negation does not only limit what can be formalized, computed, or learned. I didn't go into the learning one, but it's a related story. But it even can be used to attack what can be said to be true or said to exist, at least according to some realist accounts. For example, this sentence is false and can be used to challenge the view by which the so-called correspondence theory of truth, by which a sentence is true if and only if it corresponds to a state of affairs of the world. But that's a fairly muddy terrain. And it depends on what you read and who you read. I'm trying to illustrate the even broader scope of this paradox. The bottom line is that if no system can thoroughly talk about itself, then nothing can be ultimately universal. So that's what I would call the tension with unreachability. And let me briefly mention that I believe that this spills into philosophy, and that this is explored in this one of my favorite books, Beyond the Limits of Thought by Graham Priest, where, well, essentially he analyzes how problematic it is to claim that something is unreachable or inconceivable or unthinkable or ineffable, because you're trying to state something that is beyond your own limits, the limits of what you can reach, you can conceive, you can think of, you can speak of. And so it's interesting and illuminating, I found, to go through the various philosophical philosophers who made such claims and attack them from this perspective, such as Parmenides, what is not, cannot be, nor be thought of. Well, here we are thinking about it. Or nothing can be known. Well, then that statement should be unknowable. Or that statement is of a different category. Something is not quite right. Or the opposite, not the opposite, but a kind of in a similar spirit, everything is relative, then, well, then so should that very fact be. Otherwise, how do you have access to that absolute truth? Or something is an indescribable, maybe like the nomen in Kant, or like admits no attributes. Well, then that very statement is an attribute. Like saying that it is indescribable is reaching beyond your own limits. Or something cannot be predicated, goes along a similar line. This is my last slide of this brief philosophical excursion. These contradictions tend to have this structure that Priest calls schema T, by which, on the one hand, something is contained within a set. On the other hand, usually by construction, this something transcends this set. And finally, this something is claimed to exist. Now, this is a contradiction, because if something exists, you expect it to have some consistency relations. It's either within or outside of a set. What's interesting is the different reactions I find to this contradiction. Endeavors based on logic, which includes mathematics, computer science, theoretical physics, and very many, almost always opt for denying the existence of that thing. It's like in Cantor's theorem. You don't want to accept a contradiction, so what must be wrong is that that thing existed. In philosophy, it's just more delicate. I guess you need to analyze the various cases. Things are not so clear-cut. For the physical world, I think people jump very fast to conclusions, but in fact, one should be more careful, because the conclusions will depend on the relation between the abstract and the physical world. And that's kind of a metaphysical problem. What do you think that relation should be? But we tend to believe that the physical world does not tolerate contradiction. And what's more interesting is that some forms of arts couldn't care less about such contradictions. They're just not bothered. And they often jump into the contradiction without any fear. Perhaps my favorite example is the movie Otto e Mezzo by Fellini, where the main character, Mastroianni, played by Mastroianni, is like the director of the very same movie. And he's kind of entering and exiting the movie during the movie. He's kind of running castings for actresses that later appear in the same movie, and so on. Like the very title is self-referential. And I use that to illustrate that something really special seems to be going on in our minds or in some part of our human condition, by which I'm not saying that I can thoroughly talk about myself. Certainly I cannot do that, or I don't have self-transparency, but I can engage in self-reflection. And in a sense, it feels like I can transcend while enclosing myself. I've tried to write several ideas in this direction in various chapters, but maybe that's all I can say at the moment. All right, so let's move to more conservative terrain. And let me now focus on our comparison between spin models and automata. Remember that our ultimate goal is to understand the relation between forms of universality. Here what we do is to cast a spin model as an automaton or a machine, which does the following job. It gives energies to spin configurations. Generally, a spin model is a Hamiltonian that assigns energies to spin configurations. And we see it as a machine, automaton, that does this job. But I like the word cast because there are some choices to be made in seeing spin models as automata, and they will influence some of our conclusions, and you may like them more or less. But that's what we do. I mean, they are different mathematical objects, right? So there is some violence that is to be done in seeing one as the other. Okay? And this goes into this casting. And what we find is that all spin models correspond to linear bounded automata, which are a weaker type of automata than Turing machines. And Turing machines have universality, but linear bounded automata do not. They might have a weaker form of universality, whereas some spin models have our form of universality. So that's a hint that the universality here corresponds to a weaker form of universality for automata. Okay, so let me be a little more precise. Technically, we cast spin models as formal languages, which are the kind of mathematical object accepted by an automaton. Namely, a spin model H will be, this arrow here will mean cast as a formal language L sub H as follows. H is a map from a domain, which are essentially a set of spin configurations to energies. And the formal language, L sub H, which we call the language of a spin model H, will consist of all pairs x comma h of x, such that x is in the domain. So all pairs of spin configurations followed by their corresponding energy, but for all elements of the domain. Okay. So in fact, this is called the graph of the function h. It's the set of elements where the function is true. For instance, the 1D Ising model H is a map from a string of +1s and -1s, which we call a spin configuration, S1, S2, up to Sn, to a number, which is given by the product of Si times Si plus 1, that is +1 if they are both pointing in the same direction, and -1 otherwise, and then you sum from I equals 1 to n minus 1. So that gives you a number between something like n and minus n. But now crucially, okay, this must be, this map is defined for all such spin configurations and for all n. This is absolutely crucial for this endeavor. That the fact that this is defined, that this family is infinite, and therefore the domain is infinite. If the domain were finite, then my following statements would be trivial or moot or pointless. Because, so following with our example of the 1D Ising model, then L sub H here would be the set of all such spin configurations, comma, or some special symbol, and then their energy. Okay, that's a number written somehow. The easiest way to write it is in unary. You could also write it in binary. Binary is a little harder to read, and some of our conclusions will depend on that. We also investigated that, but for now, just consider it's a number. But now, crucially, for all spin configurations and for all n, you see, if this domain were finite, then my language would be finite. And all finite languages are regular. They are trivial. Because what I then do is I investigate the complexity of such a language in the eyes of the Chomsky hierarchy, or through a generative grammar. Namely, what we do is we classify LH in the Chomsky hierarchy. And now we prove a theorem. So this is not to be discussed, or like if the theorem is correct, then this is a fact, as opposed to whether you like more or less disgusting. Once LH is defined, then you can really say, well, look, it is deterministic context-free. I'll say in a second what that means. So as a byproduct, this provides a new complexity measure for classical spin models, which captures the hardness of the grammar of physical interactions. I like this idea. The grammar of physical interactions, when a formal language, LH, can be, in the Chomsky hierarchy, can be a regular, deterministic, context-free, context-sensitive, recursively enumerable, or in fact, most of them are outside of this, are like just too wild to admit any sort of grammar. Because these are the sorts of languages that are recognized by some automaton. The best known one are Turing machines, which recognize recursively enumerable languages. But then linear bounded automata, which are like Turing machines with linear amount of tape, they recognize context-sensitive languages, push-down automata, context-free languages, deterministic push-down automata, deterministic context-free languages, and finite state automata, regular languages. Okay, each is strictly included in the next superset, And they can alternatively be characterized by a type of grammar, generative grammar, that gives rise to all strings in the language. Our classification says that spin model H, if it is one-dimensional, meaning that the spins are placed on a one-dimensional physical distribution, then they are deterministic. Their corresponding language is deterministic context-free. If they are zero-dimensional, which means that they are finite, then they are regular. That's trivial. It's also true if they are effectively zero-dimensional, which just means that their energy depends on a finite amount of spins at either end of the chain. Regular languages essentially, or finite state automata essentially do pattern recognition. Patterns must be finite, so they can recognize that. But now what's more interesting is that 2D or higher D or all-to-all or really any general, very general definition of a spin model we could come up with, all of them were such that their corresponding language was context sensitive and never recursively enumerable. So this is our hint that there's a mismatch of universalities. These are not universal, and this may or may not be. The 2D without fields is not universal in our sense. The 2D with fields is. As a byproduct, as I said, we find a different complexity classification of the eating model with a different easy to hard threshold. Usually one considers the computational complexity of the ground state energy problem, which is NP for the 1D and 2D Ising without fields, and NP complete for the 3D Ising or 2D Ising with fields. In our case, the threshold is between 1D and higher than 1D. 1D is easy, deterministic context-free. Higher than 1D is hard, context-sensitive. Ultimately, because a string, so languages are collections of strings, of elements of a finite alphabet, and strings are one-dimensional objects. So if your spin configuration was originally a one-dimensional object too, well, you can read its states and kind of compute its energy with a push-down automaton, which has a kind of a Keller, like stellar that stores the energy. But if your spin configuration was a two-dimensional object, like in a 2D Ising model, you need to stretch that configuration as a string. And that's doing some real violence to the mathematical object in the sense that suddenly you will now have long-range correlations, where long means arbitrarily long as n grows. And this results in the fact that you need a linear bounded automata. All right. Let me say a few words about a comparison between spin models and restricted Boltzmann machines, deep Boltzmann machines, and deep belief networks. In this case, the results are a lot clearer. We show that the two notions of universality are essentially the same, or more precisely, that the universality of machine learning models follows from the universality of spin models. They were independently discovered, and yeah. So more precisely, a universal spin model. So I think blue here denotes visible units or physical spins, and red denotes hidden units or auxiliary spins. They're essentially the same. And the idea is that a universal spin model can simulate any other spin model, where simulate has a precise and fairly long mathematical definition, but it essentially means that it preserves the low energy sector. And as a consequence, it approximately preserves the Boltzmann distribution up to an error that will decrease exponentially with a threshold delta. This threshold delta is what defines the low energy sector. So below delta is your low energy sector in the spin model. Above delta is your high energy sector, and of the extra stuff that you don't want to take into account. Okay, so we have on the one hand this statement that there are such things as universal spin models. On the other hand, it has been proven that some machine learning models, like restricted Boltzmann machines, can approximate any probability distribution. In that sense, they are a universal approximator. What we prove is that if the underlying spin model of our machine learning model is a universal spin model in our sense, then it will also be a universal approximator in the sense of machine learning. Okay, so this notion of universality for spin model entails universal approximations for machine learning models. And a further thing we learn is that for spin models from the world we're coming from, we have characterizations, namely theorems that say, look, a spin model is universal if and only if it is flat complete and closed, or there are some two properties can be expressed in various ways, but we have good control of these properties. And this theorem of ours, when translated to the machine learning setting, provides new universal approximation theorems for restricted Boltzmann machines, deep Boltzmann machines, in a more nuanced way for deep belief networks. And this provides a unified approach to all such universal approximation theorems based on sufficient conditions, based kind of on the insights that we had obtained from our thorough, fairly careful analysis that Toby Reinhardt did in our original paper, studying many properties of simulations, such as their modularity, many of the things that are preserved. It's like a 50-page paper, very careful. It's mainly the work of Toby Reinhardt. All right, and finally, let me say a word about our framework for universality. First, a disclaimer, it is in fact a categorical framework, so based on category theory, but I will say nothing about category theory. I will just try to convey the idea and the examples encompassed by this idea. So we're trying to define universality abstractly. So we set up an abstract world, that is to say, a category, where there's things called targets and contexts. Targets are things like functions, and contexts are inputs to these functions, for example. You can think of them that way. Now, a simulator will be a map from targets and contexts to targets and contexts, which can have the property of being universal if it encompasses all targets and contexts. Let me say in a second what encompass can mean. Encompass could mean be. That is what the trivial simulator does. It will be universal by just being all targets and contexts. It's like saying, imagine that targets are Turing machines and contexts are inputs to those Turing machines. Well, the set of all such Turing machines with their inputs is universal in a trivial way. But some simulators are universal in a non-trivial way. They have a notion of pretending to be, or mimicking, or simulating all targets and contexts while not being them. For example, the universal Turing machine can simulate any target Turing machine, or the universal spin model can simulate any target spin model. And so the underlying idea is that sometimes you can pretend to be in more efficient ways than by being. That's one way to see universality. As examples, of course, we have our guiding examples, universal Turing machines and universal spin models, but also things like that a set is dense in another, like the rationals are dense in the reals. That's a way how the rationals can pretend to be the reals. For any real and precision, there is a rational that is at most at that distance, at that precision from the real. It's pretending to be, would be given here by the precision. But also the basis of a vector space. A vector space has infinitely many points, usually, but its power, its beauty, its use largely lies in the fact that you can capture all of these points by a smaller set, say a finite set if it's finite dimensional, which can generate by means of scalar multiplication and addition, linear combinations, can generate any point. In this sense, the basis of a vector space can pretend to be all such points and is therefore universal in a non-trivial way. Or NP-completeness, a decision problem that is NP-complete can pretend to be another decision problem in the class NP. Right? Like if you take Max Cat, it can pretend to be the traveling salesperson problem. How? Well, via the reduction from the traveling salesperson problem to Max Cat. The reduction is telling you which instances of Max Cat you should be looking at. Yeah, that would be the notion of pretending to be in that case. There are more examples. Top of a preorder, a generating set of a group. This would also be examples of universality. And we also prove some general theorems in the framework, not just examples, as well as a relation between universality and unreachability via Louvier's theorem. Okay, so with that, I've been talking about our endeavors to understand some of the scope of notions of universality and unreachability concerning our ideas, the comparison between spin models and automata and machine learning models, and finally, our framework for universality. But I'd like to add with a more open question for this very interesting audience, which is whether universality and unreachability, or this line of thought, can shed light on thought or the mind. I've been reading a lot of books in recent years to try to find my way through this question, and it's quite complicated or not very straightforward. So I'm looking forward to learning from you whatever insights you may have in this direction. An underlying question I believe is very interesting here is to what extent is to think to compute? And I'll leave it here. Thank you.
Thank you very much, Gemma. We're going to have time for 2 questions from the audience. Julia, and there's someone there. Elisa, yes. Okay, so Julia? No? Yes. Go ahead.
Well, thank you so much. I am very impressed. I cannot say I follow completely, but I'm very interested. And I wanted to ask you, you know, Hopfield has just got the Nobel Prize last year. He started in solid state physics working with the Ising model, and then he finished in machine learning. Is there any of this discussion that you have mentioned involved in his thinking when he does his approach that gave him the Nobel Prize? I just read a paper on saying what happened to solid state physics, okay, going to complexity. And I wonder if this sort of discussion that you have presented has something to do with his development.
Perhaps I can, thank you for your question. I may not be able to directly answer your question, but maybe provide some more general reflections. Hopfield networks are a very simplified model of the brain, like artificial neural networks, that see the processes in the brain as a certain computational process. And this is mathematically similar to how the dynamics of a spin model. There are nuances, right? But can be seen. So that would be one part of the answer. Another part may be that what's interesting in these various examples that we've been considering and that we're not talking about is that often a small amount of complexity suffices to generate or to encompass all features of a set. And this is really what I've been after, trying to understand that the crossing of that threshold. So often these very simplified models already can reach very far in terms of what they can do, right? Like these machine learning models, they just have these Ising interactions and this restricted interaction connectivity pattern, yet they suffice to approximate any continuous function in essence. And that's kind of the question that's burning in me, like why is it the case that fairly simple structures are powerful enough to emulate an entire set? I'm not sure if this reflection extends in any way to solid state physics. I don't know.
Tenemos una pregunta ahí atrás y luego aquí Humberto.
Thank you very much for a very interesting talk. So you talked about the language of physical regulation, something like this. And I'm wondering if you have any thoughts on biological complexity. So basically there is like this open question if the cell, not going as far as the brain and language and so on and so forth, but if the cell can be thought of as a machine. Do you have any ideas about it?
Thank you for your question. So my excursions into biology have taught me that everything is a lot more complicated than in our beautiful physical world. That being said, of course, we'd like to use insights from computer science and automata to shed light on aspects of the workings of the cell, or more generally of other biological systems. And I have a concern that affects both biology and physics when it tries to take seriously the lessons from computer science. And that has to do with the central role played by the unbounded in computer science. Like the fact that the tape of the Turing machine is unbounded is central. I can say more about that in the round table, perhaps. And that has, in my opinion, no role to play in physics, but even way more clearly in biology. It's sort of ridiculous that one takes, I guess, asymptotic scalings of functions and so on. So maybe my overall answer is I'm not sure how many meaningful things we can learn from computer science when applied to the biological examples you had in mind.
Seguimos con Humberto. Aquí tienes el micrófono.
Thanks, Gemma. You said that in your last question, whether your approach could connect with thought. If that would be right, what do you imagine could be the connection, and what it would mean for computer science, or for this last question, where people wonder whether our nerve system is working computationally?
So the question is very open and very difficult, and there are many angles from which to tackle it. I can answer it from one particular angle that we have considered, and that has to do with the role of contradictions in the mind in comparison to a computer. And more precisely, the fact that the halting problem is uncomputable, as I said, is often proven by assuming it is computable and generating a contradiction, and then rejecting the contradiction, and then concluding what we wanted. But the mind can follow this proof and not be stuck in an impossible state of 0 = 1, or of it doesn't fall, it never enters the situation where a portion of the brain is in 2 different states at once. And for this reason, some people have concluded that the capabilities of the mind are superior to those of a machine. I believe in Roger Penrose in The Emperor's New Mind, Douglas Hofstadter in Gödel Bach, and I believe that both were very influenced by a little book by Nagel and Newman, 1954, called Gödel's Proof, that suggests the same thesis. We recently considered this question and concluded that, well, but this conclusion is premature, because in essence, what the mind does is to unfold this contradiction in time. So it maybe follows a reasoning and says, take the liar paradox, which is the same thing, right? It's, I am a liar. And by following the reasoning, it says, yes, I am right now lying. By going on, it says, no, I am not lying. And it says, I am lying, I am not lying. So it enters this kind of loop. And eventually the mind is capable of exiting the loop. This illustrates one aspect of how the mind works differently than a computer. Another very disturbing aspect of computers, or if we care about inferences for the physical world, is its use of infinities or unboundedness. But all of that is really, in a sense, dodging the main question that you asked. I think I asked the question in such a general way that it's difficult to decide from what angle to take it. There are many possible angles.
Thank you, Gemma. Thank you very much. So we're going to start our roundtable. So please stay with us, Gemma, because you're part of it. And we will welcome Carlos Jersenson from the University of Binghamton, USA. Paul Strader, I hope I'm pronouncing okay. Okay, yes, from